Let's start with chapter 1. Chapter 1 deals with measurements and units and a bit of kinematics. So the first and foremost thing what you need to know is what is physics? Now, physics is the subject of accurate measurements where you end up measuring all the different entities. So as you go through your book, your textbook, I'm right now on page 3, and now this is the 6th edition. So from page 3 onwards, it discusses some general ideas about physics as to what it is and how physics has to be learned and stuff like that. But then we are focusing our attention to the first topic, which is physical quantities and their units. Because when you have a physical quantity, now what is a physical quantity? A physical quantity is anything that can be measured. Anything that can be measured is a physical quantity. So let's start jotting down. Physical quantity is anything that can be measured. And when you measure something, you need to express it in terms of a unit, because when a measured quantity is to be expressed, you need a standard to express it. For example, if you want to measure the length of the room and if you don't have any tool to measure with, you can always use your feet and just check how many feet it covers. Or you can just use this piece of paper and find out how many of these papers will fit in there. But we need some kind of a standard. Now, different standards have come and gone. Like you had inches, you got centimeters, you got grams, you got pounds, you got ounces. There are different kinds of units have come and gone, but most of them are not used these days because they don't make any scientific sense. So units that have some scientific sense and is clearly defined, they're called SI units. SI stands for Systems International. So we have Systems International units in which you measure physical quantities. Now physical quantities are classified into two main classifications. You have basic quantities and you have derived quantities. Now, when you have a basic quantity, what is a basic quantity? A basic quantity is a quantity that stands alone to represent itself. It doesn't need the support of any other quantities. It can stand alone. And some of them are mass and is measured in kilograms. Now, kilogram is the SI unit for mass. When you say weight, weight is not mass. Weight is a force of gravity, and we measure it in a different unit altogether. We measure it in newtons, as we'll see it in other chapters. The other quantities are length, and is measured in meters. Now, there were days when length used to be measured in units called chains and different furlongs and so many different kinds of units, but they've all gone because, as I said, it doesn't make any scientific sense. And that's why length is nowadays defined properly in scientific terms, and therefore length is measured in meters. Like you must have heard about yards, inches, feet. They don't make any sense scientifically. If you want to know what is yard, yard apparently is supposed to be the distance between the tip of the nose of a king, King Henry, to the tip of his thumb. So he stretched out his arm and asked people to measure it, and it was measured using a stick, and that was called a yardstick. He instituted this yard, and some countries are still following this yard, which is very strange. But then most countries actually are using meters and systems of this kind. Now, if there are more than one length, like in area, because it's length times length, the unit is meter square, and so we call it derived. So what is derived? It's made up of two or more basic units. So derived is made up of two or more basic units, and basic stands alone. Now the next one is time, is measured in seconds. And then these are the three prime quantities that will find its place into any, literally any chapter. But then there are some basic units which are mainly for certain chapters, and they are temperature. Temperature is not measured in degrees Celsius or Fahrenheit, it's measured in Kelvin, because Kelvin makes more scientific sense. So if you want to compare, if you want to see what is Kelvin and how Kelvin makes better sense, you can actually look at it this way. Imagine you have two containers. You have a container here, ice cold, and you have another container here, which is boiling water. Now that is 100 degrees Celsius, and that is 0 degrees Celsius. So if I ask you a qualitative question, is this hotter than this? And you'll say yes, and that's correct. But if I ask you how many times hotter is this compared to this, we won't be able to give a certain number. If you say this is 100 times hotter than this, 100 times 0 will be 0. So it doesn't make sense. And so that explains why the Kelvin temperature, Lord Kelvin designed the temperature scale in terms of energy. According to his scale, this is 273 Kelvin, and that was 373 Kelvin. Now if you say, is this hotter than this? Yes. How many times hotter? Not even 1.5 times. So 373 is not even 1.5 times hotter than this. So as you keep going down lower and lower and lower, you get to 0 Kelvin. That's called absolute zero. So Kelvin makes better sense. And so that is temperature. And the other quantities are quantity of substance. Quantity of substance is measured in moles. And then electric current. Electric current is measured in amperes. Light intensity is measured in candela. Now, obviously, this one is going to appear more in thermal physics. This will come up when you discuss about gases. This will come up in the chapter of electricity, and this one comes up in light. Beyond this, there are some subsidiary units, which are angle. Angle is measured not in degrees, it's measured in radians. Now there are different kinds of angles. We have a solid angle and a plane angle. Plane angle is what is measured in radians. Solid angle is measured in steradians. We don't require that for this course. Also, we won't be discussing this. So light intensity is also not going to be discussed in this course. Now, coming onto this side, the list is over. That's it. There's no more basic unit in any subject, whether it's biology or chemistry or anywhere. You won't find any more of these basic units and basic quantities. Any quantity that you're going to say from now on is going to be derived, like speed, acceleration. Everything's going to be force, momentum, energy, pressure, and this list is endless. This is an endless list because you have thousands and thousands of these. These are just the basics. Now the other thing you should know is when you measure any quantity, you're going to express the physical quantity. So physical quantity is going to be expressed in terms of a number and a unit. In fact, it is a product of the number and the unit. It's a multiplication product of number and a unit. For example, if I say the mass of something is 5 kilograms, then it actually is 5 times a kilogram. So this means it's 5 times 1 kilogram. Now, when you have a product of something, when one of them goes down, the other has to go up in order to maintain the same product value. Like for example, 100 times 1 is 100. If you make this one go to 2, then this becomes 50 to make it 100. If you make it go to 4, then that becomes 25 to make it 100. If you make it a 5, it goes to 20 to make it 100. And if you make it a 10, that goes to 10. So you can see as this goes increasing, this goes decreasing. It's inversely proportional. So the number and the unit are inversely proportional. Keep that in mind. So when the unit goes bigger, the number has to go smaller. When the unit goes smaller, the number has to go bigger. Like, for example, if I change this to grams, now kilogram is going to gram, as you know that gram is much smaller than a kilogram. How many times smaller? 1,000 times smaller. And therefore this number has to go up 1,000 times. So it becomes 5,000 grams. So this is how we do the conversions of units. So expressing in one unit and then later on deciding to change the units, you have to keep this in mind, the inverse proportion. When one goes up, the other has to go down. Okay, now let's move on to what we call as the prefixes. Well, before you go to prefixes, let me go to scientific notations. So what is a scientific notation? A scientific notation is a way to express a number. When you measure a certain number, you want to express it in a certain format. And the format that you need to express. And the problem with why do we need scientific notations? Let me give you an example. When you do a calculation, just like that, when you do a calculation, such as 1, 2, 3, 4 times 5, 6, 7, 8. Sorry. 1, 2, 3, 4 times 5, 6, 7, 8. If you're going to multiply this, you get a number which is, so 1, 2, 3, 4 times 5, 6, 7, 8 gets me 7006652. Now when you have numbers like this, when you want to transfer it from here to here, there is a chance that you make mistakes with these zeros or the number of sixes. Some mistake is possible, and these mistakes can be very serious, because imagine a zero is missing, so that becomes a serious mistake. Now to understand the seriousness, let me tell you this. Imagine you got a lottery for this amount. Now this amount is $7,006,652. Imagine you got this lottery, and the person who wrote the check missed a zero, wrote it as 706652. Is this okay to excuse that mistake and go on with this? Now you can see very clearly this is only $706,652, whereas you were supposed to get 7 million. And naturally that mistake is definitely costly. So to not make such big mistakes, in the scientific calculations, we express these numbers in what is known as scientific notations. And scientific notation for this, for any scientific notation, we write one digit, decimal, other digits, and then times 10 to the power of one more digit. So if you have to express this in this format, I will have to write it as 7.00, and the next digit is 6, so I can round it off to 1, times 10 to the power of, this is going to be 6 places, so this. So expressing it in this fashion is what we call as scientific notation. So when you do calculations with the calculator, it's ideal to express answers in this fashion, and that is why scientific notation is important. And your calculator can do it for you. And what do you do to set your calculator to scientific notation? All you do is press the mode button once, and then you can see that it is flashing on the normal. Scoot to the right to scientific, press enter, press clear screen, press enter. Now you can see the number that is displayed is 7.006652 E6. Now E stands for the same as 10 to the times 10 to the power of. E stands for times 10 to the power of. So 7.006652. Again, you have all these numbers, but one good thing is, if somebody makes a mistake here and cuts off this 2, forgets to write the 2, you still have 7.00665 millions. What about 5 also is missed out? You only lose $52. It's fine. If this is also not there, you lose only $652 out of the 7 million. Still tolerable. And even if you take this out, you're still fine. Now, your calculator can do the rounding for you. Instead of you doing the rounding, the calculator can do it for you. For that, what you do is press the mode button once, and you can see the second line which says float. Go down to the float, and then you go to the right 0, 1, 2, 3, 4. How many decimal places do you need? Go up to there. So if I need 2 decimal places, I go to 2, press enter, press clear screen, press enter. And you get this number, which is exactly this. Now this has got 3 significant figures, 1, 2, 3. 3 significant figures, 2 decimal places. So expressing it in this fashion is called scientific notation. Okay, so, and then comes the order of magnitude. Now these are all the foundation topics. So once you know these foundation topics, you should be okay to continue with physics. And you'll feel comfortable. All right, so what is order of magnitude? Order of magnitude is after you express a number in scientific notations, you look for the 10 power. That is called the order of magnitude. So that one is the order of magnitude. So in this number has got the order of magnitude of 6. Like for example, what's your height? Expressed in scientific notations. So for example, my height, if I have to express my height, I'm say 174 centimeters. So 174 centimeters, but centimeter is not the right unit. I need to express it as 1.74 meters. But how do I write this in scientific notations? It's 1.74 times 10 to the power of 0. So 0 is my order of magnitude for my height. So that is the order of magnitude. And for example, another example is, let's take a building. If the building has a height of say 65 meters, then how do you express it in scientific notations? We write it as 6.5 times 10 to the power of 1 meter. So the 1 is the order of magnitude. So I hope you understand what order of magnitude is. Okay. So you know scientific notations and you know what is the order of magnitude. And now let's move on to what is known as prefixes. Prefix. What is a prefix? It is the letter that comes in front of a number. It's a letter that comes in front of the number, front of a unit. So that's called a prefix. And why do we write prefixes? We write prefixes in order to make things easier to express. So instead of writing a lot of 10 powers, we make it shorter or bigger. So any small number, suppose it's a very small number, you like to write some prefixes for it. If it's a very large number, also prefixes will help. And so throughout our course, you will see numericals thrown to you with different kinds of units and maybe different kinds of prefixes. And you need to know exactly what each prefix stands for so that you can actually work your problems out. Okay? So to start with, if I take the simplest thing, for example, 1 meter. If I take a meter, how do you express the meter in scientific notations? I'll have to express the meter in scientific notations as 1 times 10 to the power of 0 meters. Now, when you have 10 power zeros, we just call it meter. So, no change. Whereas if you have a number that is 1000 meter, now 1000 meters is 1 times 10 to the power of 3 meters. And this times 10 to the power of 3, we replace with the letter K. So we call it kilometer. Now, if the number is bigger, then you write 1 times 10 to the power of 6 meters, and we call that a megameter. And then if your number is bigger, this is 1 times 10 to the power of 9 meters, and you should be able to say that. It's giga. And if the number is bigger, then this is 1 times 10 to the power of 12 meters, and that's called a terameter. And it keeps going on. Now, on the lower end, if you go below this, you can have 0.1 meters. Now, if you have a 0.1 meter, we can write it as 1 times 10 to the power of negative 1 meter, and we call that a decimeter. And if you have 0.01 meter, we call that 1 times 10 to the power of negative 2 meters, and that's called a centimeter. Still lower than that, 0.001 meter can be written as 1 times 10 to the power of negative 3 meters, and we write it as millimeter. And now from here onwards, you can see it kind of multiplies itself in terms of threes. So if it is that, it's 1 times 10 to the power of negative 6 meters. We write it as micrometer. And since micro also starts with M, we borrow a letter from the Greek alphabets, and that's mu. It sounds like a cat meowing. So it's like mu micrometer. It's like a long line with a U. And then again, if it is that, 1 times 10 to the power of negative 9 meters, and then it is a nanometer. If it is smaller than that, then we write it as 1 times 10 to the power negative 12 meters, which is called a picometer. And then if you have It's 1 times 10 to the power of negative 15 meters, and that's called a femtometer. And again, this list goes on, but we don't want to keep going. Now, which of these are actually useful to you? Probably till nanometer, micrometer, millimeter, centimeter, meter, kilometer, megameter, giga. Tera probably is not going to come up. But these are all units that can be part of your learning area. Okay, so that's about prefix. Now, so instead of writing all these big or small powers, you can write the prefix instead. Now, the diameter of an atom is approximately between these two. The diameter of a nucleus is around here, femtometer. So, the very small measurements follow this. Now, these are all bigger ones. Now, you don't have to have meter as a base every time. You can actually change this to seconds. You can change it to grams. You can change it to anything. If you're going to change this to grams, then this is going to be kilogram, and this is going to be megagram, gigagram, teragram, and this is going to be decigram, centigram, milligram, microgram, nanogram, picogram, femtogram. Now, if you're going to call this seconds, kilosecond, megasecond, gigasecond, decisecond, centisecond, millisecond, microsecond, nanosecond, picosecond, this can be time, length, or anything. You can have anything here, and these are the prefixes that actually come and help you out with these powers. Now, if you have a numerical which apparently has nanometer in your data, what you need to do is get rid of the nano and put this instead in your calculations. So that is why prefixes become pretty important. So if I ask you what is the area of something, and if I give you distances in millimeters, now you have to take this milli and change it to this. And you'll see multiple examples that we'll work through, which will explain that idea. Okay, so hope things are getting clear. Now let's go on to our textbook. The next thing in your textbook that you need to focus on is on page 17 of the 6th edition. And here it is, frequency. What is frequency? Frequency is the number of cycles of a periodic process that occurs per unit time, and it is abbreviated as F. So F stands for number of cycles in 1 second. That's called frequency. And similarly, there's another term called time period. Time period, symbolized by the letter capital T, stands for time taken for 1 cycle. So basically, if I say 1 cycle, it takes T seconds. So in 1 second, how many cycles? Did you guess it right? 1 cycle is T seconds. So in 1 second, how many cycles can you get? You can replace the word cycle with vibrations, revolutions, rotations, anything. So in T seconds you have 1 cycle. In 1 second you have how many cycles? Seems a little difficult to calculate. But if I tell you in terms of cakes and all that, you should be able to get your answers faster. Imagine this is 1 cake. 1 cake is $5. If 1 cake is $5, $1 will get you how many cakes? If 1 cake takes $5, $1 should get you 1/5 of a cake. Similarly, one cycle is t seconds. In 1 second, you can get 1 over t cycles. So the number of cycles in 1 second is called frequency. So this is frequency. So 1 over t is frequency. You can also say time period is 1 over frequency. Now frequency is measured in a unit called hertz. Frequency is measured in hertz, because you can see frequency is per second. Also you can say second to the power of -1, or simply hertz. Whereas time period is measured in seconds. Okay, so if you look at the definitions on these pages, you'll see it. Time period is defined here. Time period is defined here on page 15, and frequency is defined here on page 17. And if you look at this example, you'll probably get some idea. The mechanical stopwatch uses a balance wheel that rotates back and forth 10 times in 2 seconds. What's the frequency of the balance wheel? Frequency is number of cycles per second. So since it is 10 times in 2 seconds, in 1 second, how many oscillations? It'll be just 5. So what's the period then? If you have frequency as 5, period is going to be the reciprocal of 5. So you get 0.2 seconds. So time period is 0.2. So calculations of this kind can be important. All right. The next concept we need to go into is speed, displacement, distance, and such things. This is called kinematics. So let me get you some background information there. There are terms that you need to know. One is distance. Now what is distance? Distance is the length of the path between two locations. So between A and B, the total length of the path is going to be the distance. For example, if I go all the way like this, and if I have to travel 20 miles like this from city A to city B, that's called distance, and it's measured in meters. And there's another term called displacement, which is also measured in meters. Now displacement is the shortest distance from the starting point to the finishing point. The shortest distance from the starting point to the finishing point. Shortest distance. So which is going to be this. And notice the arrow mark that I'm putting there. The arrow mark indicates that there is a certain direction involved in displacement. And this probably is going to be like 15 miles. So the displacement is the shortest distance from the starting point to finishing point, which means it's a line of sight. Whereas distance is the actual length of the path. So probably between your school and home, you're going to travel 20 miles like that. But if you drew a straight line between your home and school, it probably is only 15 miles. So we do have to take all these turns because the road goes that way. So this is called a displacement, and that's called distance. And distance has no sense of direction, so that's why it's called a scalar quantity. Whereas displacement has a vector, has got a sense of direction, and that's why it's called a vector quantity. So quantities that have a sense of direction is called quantities that have sense of direction are called vector quantities, and quantities that have no sense of direction are called scalar quantities. So scalar, vector. Like if you say mass, that's going to be a scalar quantity, whereas weight is going to be always acting downwards, so that's a vector quantity. Energy is a scalar quantity, whereas force is a vector quantity. So you can actually classify time is a scalar quantity, no sense of direction, whereas other things like magnetic field. That's going to be vector quantity because it's sense of direction. So there are quantities that have sense of direction, and there are quantities that have no sense of direction. They're called scalar quantities. So understand vectors and scalars. Now coming to distance, we have speed. Speed is the rate of change of distance. Speed is the rate of change of distance and is measured in, so basically what it means, rate means divided by. So speed is distance over time. So rate means divided by time. Distance is measured in meters and time is measured in seconds. So speed is measured in meters per second. So you can write meters per second, or you can also set meters per second, different formats. Now speed is also a scalar quantity because it has no sense of direction. What speed did you drive before while coming from home to school? Well, you're going to say something but no sense of direction. Like if you took 1 hour to come from home to school, 20 miles in 1 hour, so your speed is 20 miles per hour. Whereas the next quantity is velocity. Velocity is the rate of change of displacement. Velocity is the rate of change of displacement. And so velocity is displacement over time. And that's also measured in meters per second. But this has a sense of direction because it is in a certain direction. So in this case, I'll say 15 miles per hour. So velocity is displacement over time and is measured in meters per second. We'll put velocity on the vector side. So you have vectors and scalars.
That was already there. Don't try to blame that on.
So velocity is coming under the vector sign. Okay, so the next thing you should understand here is coming to the speed again. Speed can be instantaneous. You can have speed can be constant or uniform. You can have speed as average. So you can have instantaneous speed, which means like you may be going at different speeds before, like for example, you take off from home and you're coming to school, you're driving at different speeds. So at a certain instant of time, what was your speed? That's actually called instantaneous speed. And in your car, the speedometer gets you the instantaneous speed. Now, uniform speed implies that you're going at the same speed every second. Every second you're moving at the same speed, and that's called uniform speed. You cover the same distance in the same interval of time. You do that, you do that, you do that, you do that. That's exactly going to be uniform speed. You're moving at the same distance. You're moving the same distance in the same time. That's called uniform speed. Now, what of your car gets you uniform speed? Cruise control. So if you put your car in cruise control, you're going to have uniform speed. Average speed implies the overall effect. Like average speed is the total distance over total time. Total distance over total time. That's called average speed. So you may not be moving at that average speed at all, but still we call it average speed. Like for example, in this case, you move from A to B 20 miles in 1 hour. Now, you probably were moving really fast from here to here, and then you kind of turned around. Probably there's a stoplight here and you stop there. So there is no speed. Instantaneous speed is 0 here. But then again, so you're changing your speed all the time and you're going fastest over here and all that stuff. So the instantaneous speed depends on where you are. Like at this point, instantaneous speed is 0 and so on. The uniform speed is if you moved at the same speed all the time on cruise control, which is not usually practical. But average speed is pretty much right. So what is the average speed between your home and school? It's 20 miles in 1 hour, so it's 20 miles per hour. So 20 miles per hour, that's the average speed. So average speed is 20 miles per hour. What do you mean by 20 miles per hour? It is 20 miles divided by 1 hour. And how do you convert this to units that you are familiar of? So 20 miles per hour, you have to change miles to kilometers. 1 mile is 1.6 kilometers. So if you want to change it to kilometers, which unit is bigger? So 1 mile is 1.6 kilometers. So which unit is bigger? Mile is bigger. So as you go from miles to kilometers, the unit is going smaller by 1.6 times. So the number has to go bigger by 1.6 times. And then this is hour. So I'll put hour. So this is going to be exactly 32 kilometers per hour. So you see how we converted miles per hour to kilometers per hour. Now, if you want to convert this further to meters per second, take that again, 32 kilometers per hour. You want to change it to meters per second. Kilometers to meters. The unit is going smaller 1,000 times, so the number has to go bigger 1,000 times. Hours to seconds. Second is smaller than hours by 3,600. So there are 3,600 seconds in an hour. So if I put that, you can actually simplify this and find out how much is 320 divided by 36. So 320 divided by 36 comes out 8.89 meters per second. That's what your speed is. So 8.89 meters per second is the average speed with which you are moving. Hope things are clear. Similarly, velocity can also be classified as instantaneous, uniform, and average. You know, the only difference between speed and velocity is that velocity has a sense of direction while speed does not have a sense of direction. And these things are explained in your textbook on these pages, speed and velocity. And you can see the average speed is defined as a total distance over total time. Instantaneous speed is a very short distance at the time that we are concerned about divided by the time. So you can see how instantaneous speed is classified or measured. And as we go on, here it defines what is velocity. Velocity is a speed in a certain direction. Here it talks about scalars and vectors. This is on page 23 of the 6th edition. It talks about scalars and vectors. And then comes the vector addition. So when you want to add vectors, what we need to do? When you have to add vectors, what do you need to do? That's what I'm going to discuss next. So Scalar addition is an easy thing. What is a scalar addition? It's just adding the numbers basically. So if I have to add 5 grams with 10 grams, I just add the numbers straight away in 15 grams. No big deal. It is an easy thing. But vector addition is not the same. Vector addition, you got to be concerned about the direction. So if I make a displacement of 10 meters to the right, and then I make a displacement of 12 meters to the left, I was here, now I'm here. So what is my displacement? So you can see my displacement is this. I was here, now I'm here. So the displacement is minus 2 meters. So when you add 10 meters and 12 meter displacements, I'm getting an answer of minus 2. And that is basically what we call as vector addition. Because you have to be concerned about the sense of the directional sense. So which way is it going? On the other hand, suppose I say here is someone is pushing something with 10 Newton force, and somebody else applies a force in the same direction of 8 newtons. So what is the total force? The total force is going to be 18 newtons because just in the same direction. But if the same thing is 10 newtons that way and 8 newtons this way, the total is going to be 2 newtons this way. So therefore, this is called vector addition. Now, it can get a little complicated if, let's look at this situation. This is a football field. You are here and your friend is here. In order to go and reach your friend, you have to walk this way first and then that way. And imagine you walked 30 meters that way. And then you walked 40 meters that way. What's the total displacement? Total displacement is going to be this distance from here to here. You were here and now you're here, so that's going to be a total displacement. We call that as a resultant. The result of this and this together is called that. Now that obviously is not going to be 70 meters. This is only 50 meters. So when you add 30 meter displacement with 40 meter displacement, you end up getting 50 meter displacement. And this we get by using Pythagorean theorem. So how do you get this? If you know what is Pythagorean theorem, you take the two legs, 30 square plus 40 square, and then take the square root, and that will get you 50. So this is what you do in case you have right angles coming in. So if you have a right angle coming in between vectors, you have to use Pythagorean theorem to get to the answer. So this gets you some ideas about vector addition. Now let's go back to the textbook again on vector addition. Here it is. It tells you how vectors are added together. On the next page, you can see here on the ship is moving at 20 miles per hour, and this girl is running at 8 miles per hour on the ship. So what is the girl's total velocity? What is the total speed? It'll appear that she's going at 28 miles per hour because you add them up. Whereas here the ship is going this way and she's running this way. So what is her speed alone with reference to the water? It'll be 12 miles per hour this way because it's 20 minus 8, 12. You can see that's called the resultant velocity. Now, in this example, there is 8 meters per second bird is flying this way and 6 meters per second wind speed. So which way will the bird end up going? the bird will end up going 8 like this and 6 like this, so it will be 10 this way. So the bird goes 10 that way. Although the bird attempts to fly straight, the bird is drifted to the right. So the bird is going to go like this. And you can see how you got this 10 is 8 square plus 6 square radical. 8 square plus 6 square radical will get you this. Now this is another example of the same bird. If the bird is going like straight and the wind is blowing like this, so the bird is going straight and the wind is going this direction, the bird ends up going here. So that's the resultant velocity. So combining it up. Now here is another example where this guy is moving this way and this way. What is the resultant? And that's what is seen here in this example. So let me stop at this point and we'll start off our next lecture of the same lesson from acceleration. I hope things are clear. If you have any questions about this, you can always email me or message me on Remind. All right.